Welcome. This is 48L Video 1. And we have a chapter now based on rotation. We're going to be spinning things. Last time we found the center of mass and things spin around their center of mass. We're going to look at various things in this chapter. We'll look at angular position, angular displacement, angular velocity, and angular acceleration. We're going to look at how angular quantities and translational quantities relate. We're going to use angular quantities to do kinematics. And then we're going to look at torque. Torque is the angular version of force. It's the turning effect of a force which is not aligned with a hinge. We'll look at moment of inertia. And then we'll also look at parallel axis rule. If we know the moment, bang. And we'll also look at torque, which is the angular equivalent of force. It is the turning effect caused by a force that is not in line with the turning axis. We'll look at moment of inertia, which is the angular equivalent of mass. It is the inertia given to a turning object by mass at various distances from the turning axis. If we know the moment of inertia of an object about its center of mass, I wonder what the moment of inertia would be about another axis. We can find that using the parallel axis rule. And then the final thing we do on this is we do rotational kinetic energy and rolling motion. So we apply these things. So let's have a look at another slide. So this is a slide where we're going to discuss angular position, angular displacement, angular velocity, and angular acceleration. And we begin by looking at a circle. Imagine a particle moving in a circle. It begins at one position and it moves s meters around the arc of the circle. The circle is r meters in radius, and that defines an angle theta. Now this angle theta is not your typical degrees. There's not 360 units in one circle if we measure an angle this way. This is your angle in radians. It's a very natural unit. It's arc length divided by the radius. The unfortunate thing is that you only get about 6 of them for an entire circle. So it's a rather large unit. People feel uncomfortable with large units. And also, it's not a whole number of radians in going around the circle once. There's 6 and a bit. So, again, people are uncomfortable by having not a whole number for a complete thing like a circle. So people tend not to use the radian very much, but if we ever meet space aliens, I suspect they won't know what a degree is, but I'm sure they'll know what a radian is. They might not call it a radian, but they'll know what it is. The thing about the degree with 360 degrees in a circle is that's our history. That's because basically in the Middle East 3,000 years ago, there was a civilization of people who were really good at math, and they had a number counting system which basically was based such that they preferred 6 and 12 and 24 and 360. And they were good at technology, so they were dominant, and when they basically subsided, other people took over that math. And so we have things like 12 months in a year and 24 hours in a day, etc. It is also very useful. I'm sorry I'm going off on a tangent here, but it is also very useful because if you try to divide 10 up, you can do 5 2s, you can do 2 5s, you can do 10 1s, you can do 1 10. There's like 4 ways you can divide 10 up. But 12, you can do 1 12, you can do 2 6s, you can do 3 4s, you can do 4 3s, you can do 6 2s, or you can do 12 1s. There's a whole bunch of ways that you can evenly divide up 12 things. So having 12 months to a year has its utilities. Anyway, enough of that. Consider a point moving in a circle around origin O. The distance along the circumference is given by S. The radius is given by R. The angle is theta radians. Every point on a rotating object has the same angular displacement. It's true that if I take a point here and a point here on the radius, they don't have the same value of S. So they don't have the same tangential displacement, but they do have the same theta. So they do have the same angular displacement. If they're at a certain position, they have the same angular position. Because they all travel together, because this is a rigid circle, they have the same angular velocity. And if they're speeding up or slowing down, they have the same angular acceleration. It's a really beautiful system. All these particles have different tangential positions, they have different tangential displacements, they have different tangential speeds, and they have different tangential accelerations. Yeah, they're related, but they're not the same. So angular is very useful at times. So let's learn some equations. So we just found out that the angle, if you like, the change in angle, the displacement is equal to my displacement, my arc length over my radius, and my angular displacement is equal to my final angular position minus my initial angular position. My angular velocity, which is given by this symbol, which is omega, is equal to, well, it's the d theta by dt, and my alpha, my angular acceleration, is equal to d omega by dt. Hold on. Didn't we used to have delta x is equal to x final minus x initial? And didn't we have v equaled dx by dt? And didn't we have a equaled dv by dt? Yeah, these are the same equations, they're just expressed in angular terms. So what we find is that we can translate between linear and angular properties, and we can do it this way. We say our arc length, our tangential displacement, if you like, S, is equal to, well, we get it from this basic equation, don't we? Our arc length is equal to theta r, our angular displacement times r, and our tangential velocity is equal to omega r, our angular velocity times r, and our tangential acceleration is equal to alpha r, our angular acceleration times r. We can even change our centripetal acceleration. Before we learned that centripetal acceleration was equal to v squared over r, well, we can substitute in for v and we end up with omega squared r. So we have two versions for our centripetal acceleration. The trick with this is to recognize that we can translate between one and the other. So basically all our equations that were linear have equivalent equations that are angular. So if we could do linear kinematics, we can do angular kinematics, and etc. And secondly, we have these bridges between the angular world and the linear world. Let's look at this next slide. So we can actually do a thing called rotational kinematics, where basically we got to recognize that what we used to call x, the linear position, is like theta, our angular position, And what we used to call delta x, which was our displacement, is now delta theta, which is our angular displacement. What we used to call v, our velocity, is now omega, our angular velocity. What we used to call a, which was our acceleration, we now represent as alpha, which is our angular acceleration. And if before we said Vf equals Vi plus a delta t, then now we'd say omega f equals omega I plus a plus alpha delta t, and so on. They translate across. In fact, we can also learn that there's a thing called torque, which has the symbol tau, which is the angular equivalent of force. And there's a thing called I know it's strange, moment of inertia, which is the angular equivalent of mass. So whereas before we said the sum of the forces is equal to ma, in angular terms we can say the sum of the torques is equal to I alpha, and it works. We can say kinetic energy is equal to 1/2 mv squared. Well, I can also say kinetic energy rotational equals 1/2 I omega squared. All this physics we've done, we can revisit in angular terms. It is really quite remarkable. Let's look at this next slide. So, a point that is 5 meters from a turning axis of a rigid cylinder has an angular velocity of 4 radians per second. So here's my point, and it's got angular velocity omega is equal to 4 radians per second. What is the angular velocity of another point that's 10 meters from the turning axis? So this here was 5 meters. So now we're twice as far away. Now it's a rigid cylinder. It's a rigid cylinder, so it has to travel through the same angle. And what we can say is, let's make a list. What we can say is that R1 is equal to 5 and R2 is equal to 10 and omega 1 is equal to 4 and omega 2 is equal to, I don't know. So I can say, oh, hold on. These points have the same angular velocity. So what we can say is that, if the angular velocity of the inside one is 4 radians per second, then the angular velocity of the outside one is 4 radians per second. If that velocity there, angular velocity there, is 4 radians per second, that velocity there is 4 radians per second, because they go through the same angle in the same time. A point that is 2 meters from a turning axis of a rigid cylinder has an angular velocity of 4 radians per second. What is the point's tangential speed? So now here's the point, and this point is 2 meters from the turning axis, and it has an angular velocity of 4 omega is equal to 4 radians per second. And then what is its tangential velocity, Vt? Well, angular Vt is equal to the angular thing times the radius. It's S is equal to angular. It's the angular thing times R. Vt is equal to angular. It's the angular thing times R. And At is equal to angular. It's the alpha thing times R. It's always angular. There's always the R at the end. So we have this Vt equals omega times R. This is equal to omega, which is 4, times R, which is 2, which equals 8 meters per second. So there's my answer for that one. And then a rigid cylinder spins about a turning axis that passes through its center. A point located 2 meters from the turning axis has a tangential speed of 3 meters per second. What is the tangential speed of a point that is 4 meters from the turning axis? So let's have a look at this. So this is 2 meters from the turning axis. And it goes like that. 2 meters from the turning axis has a tangential speed of 3 meters per second. So that's 3 meters per second. And what is the tangential speed of a point that is 4 meters from the turning axis? You can kind of see it's going to be v tangential. If this is 2 meters and this is 4 meters, you can just see by the kind of distance traveled, it's going to be linear related. The thing that is the same, remember equations are always about linking things that are the same. The thing that is the same is the angular velocity. So I can say my angular velocity times r is equal to v tangential. So what I can say is my v tangential for the first point over the radius of the first point is equal to omega, which equals, because it's the same for both of them, my v tangential of the second point over the radius of the second point. You see that the consistency of the angular velocity for all points on this rigid cylinder as it goes around and around, that's my common factor. So I say, oh, in that case then I have 3 over 2 must be equal to Vt over 4. So Vt is going to be equal to 3 times 4 over 2, which equals 12 over 2, which equals 6 meters per second. Yeah, you know, I'm twice as far from the turning axis and my tangential velocity is twice as big. There is a systematic change to it. Let's have a look at this next page. So on this one we say a point on a rigid cylinder has an angular velocity of 3 radians per second at time t equals 2 seconds. So here's the point, and it's got an angular velocity of, I do my angular velocities as like curvy little arrows, and that's 3 radians per second, and the time t equals 2 seconds. The cylinder has an angular acceleration, of minus 5. So what that says is that my angular acceleration, my alpha, is equal to minus 5 radians per second squared. What is the angular velocity after 6 seconds? Oh, interesting. So after 6 seconds, let's assume I'm here. T is equal to 6 seconds. I want to know my v, my angular velocity, my omega final. It's a bit like kinematics. It is angular kinematics. It's the same thing. So what we can do is, well, if it's uncomfortable, let's make a list. So we say, I want to find omega f, but I don't know what it is. I do know what omega I is. I was told that it's plus 3 radians per second. I do know what my delta t is because it's t final minus t initial, which equals 6 minus 2, which equals 4 seconds. And I know my alpha, and my alpha is equal to minus 5 radians per second squared. And if that doesn't jog your memory, just go back and say, well, that's like v final, and that's like v initial, and that's like my change in time, and that's like my a. And I suspect if you do that, you'll say, well, vf is equal to vi plus a delta t, because you studied it before. And if that's the case, I think the next thing you'll see is you'll say, well then omega f is equal to omega I plus alpha delta t. So that means that omega f is equal to plus 3 added to minus 5 times 4. So omega f is equal to plus 3 added to minus 20. So omega f is equal to minus 17 radians per second. Very interesting. Now let's just stop for a minute and visualize this. Well, the first thing I'm noticing is that this illustrates that I have a different direction of turning for positive going turning things and negative going turning things. And the way I draw them is positive going turning things go counterclockwise and negative going turning things go clockwise. So my minus 5 alpha, my alpha, my angular acceleration was equal to minus 5 radians per second. And when I look at that combination, when I'm looking here, I'm looking at those two. You know, this is like throwing a ball up in the air. It's going to go up, but it's slowing down. And at some point it's going to stop. And then it's going to reverse directions. So I'm not surprised that I'm getting a negative angular velocity at this point. What happened was this particle went around and slowed and stopped, and now it's come back and it's somewhere around here, kind of zooming on really quite quickly. So it's just like kinematics, whereas before up was positive and down was negative and to the right was positive and to the left is negative. It's a little bit different. Counterclockwise is positive and clockwise is negative. And we just do the problem the same way we did it before. It just works out quite nicely for us. So there we have it.